The next talk is the title Taming Reachability Analysis of DNN-Controlled Systems via Abstraction-Based Training. And the talk will be given by Zhang. And
yeah.
I'll let you introduce your co-authors.
Yeah, okay. So good afternoon, everyone. You?
The co-authors you want to
So my name is Zhang. I'm from East China University. So my talk is about how to tame reachability analysis of deep neural network control systems via abstract-based training. So this is joint work with my student and also my collaborators from Oxford University and also Guy Katz from the University of Hebrew University of Jerusalem. So as we all know now, so deep learning is almost everywhere, and so we can use deep learning to train a lot of classification tasks. So besides that, so we also can train like deep neural networks that used to control our vehicles and also devices, various of vehicles, and so most of them, so they are gradually applied to safety critical applications, and so the safety issue of such kind of systems, so they gain a lot of attentions. So there are safety issues. So in 2022, Sasha published a paper at the Commission of ACM to comprehensively to discuss the safety issues of such kind of systems. So let me just briefly give a very simple example about deep neural network control systems. So imagine that this is a Monte Carlo problem, and it's very widely used in deep reinforcement learning community to evaluate how the training approach to train some good performance controllers. So yeah, this example is very simple. So it seems that for this system we only have for each state, so it consists of two pieces of information. One is position and the other is speed. So using deep learning, so we can assume that we train the deep neural network that can make decisions on each state. That is, so giving a concrete state and the controller, that is the deep neural network, so it outputs an action that is enforced to the device, to the car, and the car will take that action and to move forward or back. So the behavior of the car is determined by what we call the system dynamics, so which is usually differentiable and also nonlinear. So we can compute, actually, we can compute the successor state of the system or the car based on the action and also the system dynamics. So the problem is, so given a set of initial states, we want to know, or we want to compute all possible reachable states in order to formally verify if the system keeps in the same zone, or if it has some interaction with some unsafe zone. So we can guarantee that we know that so there are maybe some unsafe behaviors that causes accident of the device. So the problem is, so we want to compute, giving a system, such kind of system, we want to compute all reachable state. So yeah, that's a very tough task actually. So let's first imagine that how we can compute giving can create an initial state. So how could we compute its successor state? So we know the mechanism of the controller is, so it takes that state and feed that state into a deep neural network and to compute action, and then based on that action, so and also system dynamics, so we can compute its the successor like this from S0 to S1, and the relation, the computation is based on this equation. So this is the current state, and so for each time horizon, we assume that the action so it's constant. So we can use system dynamics to compute the set state. But the problem is that, so if we are giving a set of state like S0, and we want to know after one time unit, so what's the set of successor state? Because here the set state is usually infinite and continuous, we cannot enumerate all the state and compute it. So to do that, we want to compute the successor state like we do on the concrete state. So if we want to do compute the set of all the successor states for a set of current state, so we need to know so what kind of actions for each state in SI. Because here the deep neural network, so it's almost inexplainable. So we cannot enumerate. We cannot enumerate all the states here. So the traditional way to do this is to overcome, to do some over-approximation, linear over-approximation to approximate the deep neural network and try to use some like Taylor models instead of deep neural network to compute the success state. But we observe that such kind of approach will introduce a lot of overestimation because of the over-approximation of the deep neural network. So in order to reduce such kind of overestimation, and our solution is that if we can partition the set of state into a finite set of subset, and if we can guarantee that for each subset like this here, there is one, so the deep neural network, the controller make a unique action on each set, then we can reduce this equation. We can get rid of the deep neural network to compute the successor state. That is, we can reduce this problem into the reachability problem of a hybrid system because we can get rid of the deep neural network controller. And there are several tools that can be used to compute reachable set for hybrid systems. So our starting point is, so we want to make sure that for each subset in this partition set, so we need to guarantee there is unique action. But that is almost impossible for traditional training because so the neural network, so it takes each concrete state as input, so it doesn't guarantee that property. So our solution is that instead of train the network and then partition the subset, partition the set into subsets, so we try to first divide the state space into several pieces, and then consider each piece as a whole. That is the initial the state in each partition set, so they are distinguishable to the controller. So that's our solution. So this is the traditional approach, and in our approach, we first divide or partition the whole state space into several pieces of the state, and feed each partition set into the neural network. This is a specialized neural network that can accept the set of the state instead of a concrete state. So yeah, that's our solution. Yeah, you can see the difference between the conventional training approach and also the abstraction-based training. So for in conventional training approach, so we feed each concrete state into the network, but in our approach, we feed each concrete state into a network, but in this specialized network, so we have some special layer we call the abstraction layer. So this layer, so the purpose of this layer is to transform each concurrent state or map this concurrent state into its corresponding partition subset. So in this way, we can guarantee that all the states in a partition site, so they will uniquely mapped to its corresponding partition and make the unique action. Yeah, so that's the that's the way how we can encode this abstraction layer. Like for each set, for this set, so we encode the abstraction layer like this. So this can be straightforwardly encoded like a part of network, and so notice that we don't need to train this part. We don't need to train this layer, and we before training we just fix all the possible corresponding like activation functions and the weight, and to do the transformation. And so once we train the network, so computing the reachable state becomes easier. Like giving a set of states here, assume that currently we want to compute the successor state for all the states in this part. And our way is to first partition this site into different pieces according to the actions the network makes. And then for each one, because for each subset, it has a unique action, so we can compute its successors and then combine them together. So yeah, that's the basic workflow of computing the reachable state like this. And we did some experiment, and we found that so in our approach we can compute more tight reachable state, like compared with some state-of-the-art tools. Yeah. And also, yeah, we completely evaluate our approaches on the benchmarks in this field, and we observe that for other white box, we call it white box, like VMCAI or Polar, they are white box tools. So in some cases, we observe that they have to terminate because they introduce too much of estimation, or they terminate because of timeout. But our approach can succeed in most of the cases. And we also want to know if such kind of special training cause some time overhead. Yeah, it's for the abstraction-based training, so it takes a little bit more time to train in order to get the similar performance. That is because we have a special layer, and it causes some additional computation. But the point is, we can train the specialized network and to make it have almost the same performance as the Euro networks. So here is the experiment about the under some kind of perturbations. We want to see how the controllers perform. And we also observe that such kind of abstraction may cause the explosion of partition, because for each partition we need to guarantee so it has a unique action. And this may downgrade the performance. So in order to have the similar performance, we need the fine-grained partitions that may cause the partition explosion. And our solution is that we do not assume a unique action. So we assume for each partitioned set, so we assume there exists some linear controller. So the linear controller is more expressive than the constant. So in that way, so we can get rid of partition explosion. So this solution is published on the NIPS so 23. And yeah, so that's basically all what I want to present in this talk. So basically, we introduce an abstraction-based approach for in order to train verification-friendly controllers. And actually, this is the follow-up work based on our SIGA-based training and verification published in at CAVE last year. And so there are several field work to do, like beside of interval-based abstraction, we want to introduce some more sophisticated abstractions and to train the network. And we also want to know if it's possible, like to introduce such kind of reachability analysis for runtime verification. Yeah, that's all for my talk. Thank you. Here are some references.
Okay, questions?
So maybe I have a question then.
Yeah.
This partition, so you use the intervals for the partition.
Yes, now we
And-
use intervals.
And do you take intervals of a fixed unit length, or how do you choose the length of the intervals?
Yeah, that's a good point. So actually, in our previous work here, we first introduced some coarse-grained partition interval, but we may fail to verify some properties because the decision is too coarse, and so based on the verification result, we refine the interval gradually, and then we can achieve equivalent performance as well as so make sure some properties are verified. Yeah.
And
It's kind
so,
of, yeah,
and so
refinement.
after the refinement, you guarantee that each box has a unique transition relation?
Yeah, that's the actually the property we need to guarantee like that. And as I said, so it may cause the partition explosion because so actually we cannot do the same action like for some partition. In that case, we need to partition it into two pieces. Yeah, and it may cause, if we have high dimension, so it causes the explosion.
It may cause non-termination also. Right?
Yeah. So our solution is that now we are trying to extending this assumption to be nonlinear, not a constant.
Yeah.
Yeah. In that way, so we can approximate the controller as the one we trained on the concrete state. Yeah.
Okay. So if there are no more questions, then that's great. Thank you very much.
Thank you.